Hello, my name is Mikkel, and today I will be presenting my research on feature-based added distribution detection in medical imaging segmentation models. Liver cancer is a leading cause of cancer death worldwide. One way that liver cancer can be, especially advanced liver cancer, can be treated is through radiotherapy, which relies on the precise delineation of not only the target, but also the surrounding anatomical structures. Deep learning-based segmentation models have recently been explored due to their efficiency and their accuracy. But a problem with these segmentation models is that they fail in information that they were not presented with during training. So for an example, this is a liver segmentation model that has been used thousands of times clinically and works very well in the vast majority of all cases, but it fails on a stent in A and ascites in B, which are both attributes that were not presented in the training data set of this liver segmentation model. And so the main purpose of our research is to identify and reject input that a liver segmentation model will fail on, which is commonly referred to as added distribution detection. The Mahalanobis distance is a commonly used added distribution detection technique. It was first created in the natural imaging realm, with the main idea being that if we train a classifier, we're going to extract features from the classifier for both the training data set and every new test image that we want to see if it belongs to that same distribution. We then apply the Mahalanobis distance, which is a distance between a point and a distribution, which is modeled by a Gaussian distribution. Because these features are high dimensional, due to the curse of dimensionality, we need to reduce the size of the features before the Mahalanobis distance is applied. Typically, this has been done with average pooling. The Mahalanobis distance was brought over into medical imaging segmentation models by extracting features from the encoder of a UNet architecture. But there are several open avenues and questions when it comes to the application of the Mahalanobis distance to segmentation models, namely two of them being, is average pooling truly the best way to prepare these features for the Mahalanobis distance calculation, and how applicable really is the Gaussian assumption of the Mahalanobis distance to these training features that we have extracted. In this work, we have two main contributions. The first one being proposing alternative methods to reduce the dimensionality of these features before the distance is calculated, with the best performing methods being principal component analysis and UMAP. And the second contribution is proposing a non-parametric alternative to the Mahalanobis distance for medical imaging segmentation models. This is a kth nearest neighbor dataset where instead of modeling the training images into a Gaussian distribution, we just take the distance between a test image and its kth nearest neighbor in the training dataset. Getting into the experimental setup now, we evaluated our methodology on 4 liver segmentation models. You can see what we named those liver segmentation models in orange. These liver segmentation models were based off of 2 state-of-the-art architectures, namely being the SWIN UNet R and the NN UNet. We then applied these architectures to both MRI and CTs. These 2,000, almost 3,000 CTs were taken from MD Anderson Cancer Center, and then were then tested on almost 350 images from MD Anderson. These MRI models, they are split into MRI and MRI Plus based off of 2 different data sets. The difference between these data sets is that the MRI Plus is more carefully curated. All of the training data for these MRI models were taken from public sources. And the test data set is also much larger for MRI Plus, with all 352 images coming from Houston Methodist Hospital, whereas the 27 MRIs for the MRI UNet R model were taken from MD Anderson Cancer Center. We differentiate between in and out of distribution using a 95% threshold of the dice similarity coefficient, with the idea saying that we're saying good performance is above 95% dice with poor performance below 95% dice. Even though this is an arbitrary threshold, we do present results for the median and 80% thresholds in the appendix of our paper if you are interested, but we do find that generally speaking, a 95% dice is a good threshold between if a model is going to need a large amount of, or if the image is going to need a large amount of edits before it is used in the clinic. The only exception to this 95% threshold was the MRI plus unit R model, as it did not achieve this 95% threshold sufficiently, and so we lowered it to 80%. We evaluated out of distribution detection with the area under the operating characteristic curve, which we will refer to as AUROC. We use this metric as it is threshold agnostic. So this truly shows how differentiable the distances for the in distribution and the out of distribution images are. We compared these feature-based methods to output-based methods for all of our models, namely maximum softmax probability, temperature scaling, and energy scoring. For the MRI unit R model, we also compared it to training-based methods where we had to go back and modify the training scheme of these images. And so we compared this model to Monte Carlo dropout and ensembling. Getting into the results now. We're going to first talk about scalability. And so what you are looking at here is this is the amount of time that it took to calculate the distances on the test images across all 4 models on the bottom. In red, you will see the average pooling, and in blue, you will see principal component analysis. And so principal component analysis really was much more scalable than average pooling, which I will note that these average pooling parameters, this was the best performing hyperparameters for average pooling and also the best performing for principal component analysis. When we look at all of the compared methods and the scalability, we can see that feature-based methods were especially the most scalable, with the Mahalanobis distance and k-nearest neighbors distances in blue and the comparison method scalability in red. This was especially apparent on the NN-UNet features. Now getting into out-of-distribution detection performance as measured by the AUROC, what we are looking at here is just the Mahalanobis distance based on how the features were reduced, with dark red being on raw features, light red average pooling, dark blue principal component analysis, and light blue UMAP. And we found that on the MRI datasets, principal component analysis best prepared the features for the calculation, and on the CT dataset, the UMAP dimensionality reduction technique performed the best. Now getting into the difference between the k-nearest neighbors distance and the Mahalanobis distance, we are now looking at our MRI models, and we're looking at the raw and average pooled features. So in red, you'll have Mahalanobis distance. In blue, you have k-nearest neighbors. In dark, you have the raw features, and in light, you have the average pooled features. And so for both these raw and average pooled features, changing the distance to k-nearest neighbors substantially improved the performance, which really brings into question of whether segmentation model features are actually Gaussian distributed as the field has previously presumed. When it comes to the best performing method, when we compare also to the output-based methods and the training-based methods, this very much varied across what data set we are looking at. When it came to the MRI unit R, the training ones worked the best, but again, these ones you had to modify the training scheme. When it came to the MRI plus data set, the feature-based methods performed the best. And on the CTNN unit, maximum softmax probability had the best performance, with the feature-based not too far behind. And so now we're going to go through some plots where the added distribution score, or the distance, is along the x-axis, and on the y-axis we're looking at the dissimilarity coefficients. And the horizontal line, this is the 95% threshold. So you can see how this would change the differentiation between ID and OOD and our performance if you lower or raise this threshold. And so something that's interesting when you're looking at these feature-based methods is that they assigned 6 images by far much larger distances than the other images in the training data set. This is on the MRI unit R model. And it turned out that all 6 of these images had very large tumors, something that was not present in the training data set. When it came to the training-based methods, these images were more directly assigned. You can see a stronger correlation between the dissimilarity coefficient and the out of distribution score, with the lowest dissimilarity coefficients achieving or being assigned the highest distances. When we're looking at temperature scaling and energy, which were created in the natural imaging realm to improve maximum softmax probability by further pushing the in distribution and added distribution distances apart, we can see that it actually brought them together and made the performance worse, which really brings into question how we should calibrate output-based methods in medical imaging segmentation models, and if the methods that work in classification models and natural imaging really translate into medical imaging. Okay, and then finally for this results section, I wanted to show a couple of plots of using principal component analysis. And so here, this is principal component analysis with only 2 components. In gray, you'll see the training data set for the MRI unit R, and then in colors, this is the test data set, and the color represents the dice of the model. And so we can see visually that the highest dissimilarities were more towards the middle of the training distribution, and there is a separation between these performances of the models. When we are just looking at the training data set itself, we found that even with principal component analysis with only 2 features, we can see a visual separation between the sources for our training data set. So these are 3 different public data sets that constituted our training data set. But you'll notice that these AMOS data sets were clustered into 2 different data sets. And so when we looked at this, it was really interesting because those ones that were mapped outside of the second standard deviation, if we were modeling this training distribution as a Gaussian distribution, those were actually poor quality images where they had been cropped and were of low resolution. In conclusion, we found that the Mahalanobis assistance is sensitive to dimensionality reduction, so it is important to consider a hyperparameter search and other dimensionality reduction techniques outside of average pooling, such as principal component analysis and UMAP, which we proposed, and as well that feature embeddings may not actually be Gaussian distributed as the field has assumed, and so distribution agnostic distances, such as our proposed kth nearest neighbors distances, may work better on certain features. The main benefits of our methodology is that it can be applied post hoc to any segmentation model. It is simple to implement without implementation online, and it is also extremely efficient. It runs on only CPUs in less than a second. Thank you for your time.